till now all of the concepts that we have discussed, you can consider them to be the first part of networks, okay, because we have only considered the element resistor and various laws and the basic circuit analysis techniques, okay. Now the analysis techniques, they are going to remain the same, but now we are going to introduce the elements capacitor and inductor, okay. So these are, as I have told before, storage elements, they can store energy, okay, and after we discuss, then we can move on to AC, okay, but the circuit analysis techniques, they are going to remain more or less same. First we will start with capacitor. So capacitor can store energy in the electrostatic field, okay. Now there are different kinds of capacitor, and the basic form is the parallel plate capacitor. So this will have two plates which are placed parallel to each other, okay, at some distance, say d. So if you consider a cross section, you can take that the two plates will look like straight lines, right, in the front view. So when this is connected to a battery or a voltage source, then it is going to get charged. Charge is going to get accumulated on each of the plates. The plate which is connected to the positive terminal will be charged positive. Positive charge will get accumulated here and negative charge will get accumulated here. Remember, there is no current flow in between the two plates, because in between the two plates there is going to be a dielectric medium. Dielectric is nothing but it's an insulating medium. It will not conduct any electrons. So why this plate is positively charged? Because when it is connected to the battery, all of the electrons will be attracted to the positive terminal, leaving a positive charge here. And similarly, all of the electrons here, they will be repelled away and they will get accumulated here on the plate. So here you will get a negatively charged plate. Okay, so this is the basic idea behind capacitor. So what the capacitor does is, it will accumulate charge when connected to a voltage source, okay. Now let us say the charge that is accumulated on the positive polarity be plus Q, okay, and on the negative plate it will be the same amount of charge but negative sign, okay. So we say that Q is the charge accumulated on the capacitor, okay. Now let us say the voltage that is supplied is V, then the charge accumulated is going to be proportional to the supply voltage V, okay. So greater the voltage, greater the amount of charge that will be accumulated. So now if you equate it, Q is equal to C into V, right. What is C here? It is the constant of proportionality for this relationship, okay, and this constant of proportionality is called as capacitance. Constant of proportionality is the capacitance, okay. Now the value of capacitance is dependent on the capacitor. It is specific to the capacitor, okay. So what are the parameters on which it depends? The capacitance C is equal to epsilon A by D. So D we have already seen, D is the distance between the two plates, okay. So first you can write that, where D is distance between the plates, and next A is the area of cross section of the plate. See, this is the plate, right. Now the area of cross section of each of the plate, okay, both of the area of cross section will be same. So the area of cross section of the plate is taken as A. And finally epsilon, this is the permittivity of dielectric medium present in between the two plates, present in between the two plates. So how can you write epsilon in terms of epsilon naught? Epsilon is equal to epsilon r epsilon naught, where epsilon naught is the permittivity of free space and epsilon r is the relative permittivity of the medium. And what is the unit of capacitance? Unit is farad. Next we will see what is the VI relationship of the capacitor. So we have seen a relationship between Q and V. Now we want the relationship between I and V. Okay. So the capacitor, it is going to be represented like this. This is the basic symbol of capacitor. Like I said, there will be various types of capacitors. Currently we are discussing about parallel plate capacitor. You have cylindrical and spherical capacitors as well. Okay. In cylindrical capacitors you are going to have concentric cylinders. Okay. Now one of the cylinders are going to have the positive charge and the other, it is going to be accumulated with the negative charge. Similarly, a spherical capacitor. So here also you will have concentric spheres. Okay, on one of them there will be positive and on the other there will be negative charge. But here currently we are still talking about the parallel plate capacitors only. So what is the relation that we already know? We know that Q is equal to CV. Now what about current? Current is related to the charge as dQ by dt. Now here if you substitute in place of Q, if you write C and V. C is a constant but V can be a variable quantity. If it is not variable, then simply dV by dt is 0. That is another issue. But it can be variable, so you can write as C dV by dt. Okay. So this is the relationship between the current and voltage. I is equal to C dV by dt. Now we need to find out the other way round as well. That means V in terms of I. Okay. So you just have to integrate. So if you integrate, you are going to get V of t is equal to 1 by C integral I of t dt. Okay. So if you are integrating from some initial time t0 to t, then you don't have to worry about the constant. Okay. Otherwise you can write or V of t is equal to 1 by C integral I of t dt plus Q of t0 by C. Okay. So that means the initial charge divided by the capacitor. So this is going to be the relationship of V in terms of I. Okay. And the first relation we saw, that was I in terms of V. Now linearity. So we already know when we discuss the resistance, we also discussed that the capacitor and inductor, they are both linear elements. Okay. And here we will get a brief idea as to why they are linear elements. So what are the two principal properties that need to be followed? The first property is the homogeneity property and the second property is the additivity property. So what is the VI relationship? We will take the relation I is equal to C dV by dt, because differentiation is easier to deal with than integration. Okay. So that means we will take V of t as the input or the excitation and I as the response. Okay. So that means according to homogeneity property, if input is some k times V of t, then input also should be k times I of t. Okay. So we will see if that is really the matter. So I is equal to C into d by dt. This is the new I dash, let us say, the new V dash. Okay, dV dash by dt. So V dash is nothing but k times V of t. K you can take out common because it is a constant. So k into C dV by dt. C dV by dt is nothing but the old current. So you are going to get Ki. So homogeneity property is satisfied. Next, additivity if you take. So what does this say? If I1 is the response due to V1, that means I1 is equal to C dV1 by dt. And similarly I2, another input, another response is C dV2 by dt. Okay, for V2 input, I2 will be the output. Now what will be the output for V1 plus V2. Okay. So, V dash if you take as V1 plus V2, then I dash is equal to C dV dash by dt. This is equal to C into d by dt of V1 plus V2. Now, differentiation can be expanded like this, right. Now, what is C d1 by d2? It is nothing but I1 and this is I2. Okay. So, for the input V1 plus V2, you will get the sum of individual outputs I1 plus I2. So, additivity is also satisfied, homogeneity is also satisfied. So, that is why we say that the capacitor is a linear element. Now, what about the power and energy relationships? Okay. So, first we will start with the power. So, we know that the instantaneous power P of t is equal to V of t into I of t. Now, I of t you can write as C times dV of t by dt. So, this is the relation, CV dV by dt is the power, the instantaneous power. Okay. Now, from here we can get the expression for energy as well, right. What is energy? It is the integration of power over a time period. Okay. So, here you have integral P is CV dV by dt into dt. This is P dt will give you this. Okay. So, you are going to get integral CV dV. Okay. So, if the voltage is being integrated from V1 to V2, then what you are going to get? Half into C V2 square minus half C V1 square. Okay. If the initial voltage is 0, if initially there is no voltage, then what will be the energy? It will simply be equal to half C V2 square, or you can simply write V square, where V is the final voltage that is present. Okay. Voltage across the capacitor. Also, if you want to write in terms of Q, then you can write V is equal to Q by C, right. So, you are going to get Q square by 2C. Now, there are some important properties of the capacitor. So, we will see what those are. The first one is that it will act like an open circuit to DC. Okay. So, because we know that I of t, the current through a capacitor, is equal to C dV by dt. So, that means if this is constant, then what will be dV by dt? It will be 0. That means I is equal to 0. Okay. So, for DC voltage, current is equal to 0. So, this is what we call as the open circuit condition. But one important point to know here, this is true only in steady state condition. So, there are two conditions, transient and steady state. Steady state is the one which will remain after the transient will pass, right. So, we will discuss more about transients later, but for now you just remember that at steady state the capacitor will act like an open circuit to the DC voltage. Now, the second point is the voltage across capacitor cannot change instantaneously. So, this is one very important point, or you can say instantaneously. Okay. Why is this the case? Once again we will go to the VI relationship, C dV by dt. What is meant by an abrupt change? Abrupt change means there is change occurring in infinitesimally small value of dt. Okay. So, that means dt is almost equal to 0, right, because that is what is meant by abrupt. Abrupt means in a very small amount of time. So, the limiting case is dt is equal to 0. So, when dt is equal to 0, this means that this entire value will become infinite. Okay. So when dt tends to 0, then I is equal to C dV by dt will tend to infinity, and this is not possible, which is not practically possible. So this is the reason voltage across capacitor cannot change abruptly. Okay, so this is one important property. Next, now this is not exactly a property. How do we represent the ideal capacitor? So the ideal capacitor is one in which the VI relationship is given by I is equal to C dV by dt, but this is not going to be the case always. There will be some leakage resistance. See, if you remember, I told that there can be no current flowing in between the two plates, okay, but sometimes some amount of current will flow, okay, and in order to show that, we show a resistor in parallel with the capacitor. Okay, so now what happens is this entire setup we call as the practical capacitor. Okay, and the resistor we call it as leakage resistance. Okay, that means a small amount of energy will be dissipated here. Small amount of energy will be dissipated, whereas in an ideal capacitor no energy is dissipated. Okay, energy will can only be stored. So now what will happen to the VI relationship here? Now here, if the voltage is given by V and the current flowing is I, then here I is no more equal to C dV by dt. Okay, so it will be equal to this I will be equal to this. Okay, so this will be the C dV by dt value, and here V by the leakage resistance will flow. Okay, so this is going to be the new relationship between I and V. Now we will do a couple of questions to get acquainted with capacitor. Okay, so voltage across 10 microfarad capacitor is given as 20 cos 200t. Find the current through it. So this is direct question, right? So what is the current through capacitor? This is given by C dV by dt. C is given as 10 microfarad, so 10 into 10 to the power minus 6. D by dt of V of t is given as 20 cos 200 t. Okay, so this is going to be 10 into 10 to the power minus 6 into 20 into 200 minus sine 200 t. Okay, so the final answer you are going to get minus 0.04 sine 200 t, and what will be the unit here? Amperes. Now next, another question. Here it is given that an initially uncharged 1 millifarad capacitor has current as shown. Okay, so this is the given relation between I and t. Find voltage across it at t is equal to 2 milliseconds and 5 milliseconds. Okay, so in the previous case the voltage was known, we had to find the current. Here current is known but in the graphical form, and we have to find out the voltage. Okay, so you can pause the video and you can do it for yourself first and then see the answer. Okay, so what is the voltage? Voltage, it is equal to 1 by C integral I dt from t1 to t2. Okay, so if limits are taken, we don't have to worry about the constant. Okay, so now this I of t is from 0 to 2 milliseconds, there is one relation, and from 2 to 6 milliseconds there is going to be another relation. So first we will write the expression for I of t. From graph, I of t is equal to some value for 0 less than t less than or equal to 2 milliseconds, and this is equal to some other value for t greater than 2 millisecond. Okay, now what is the equation of this line? Okay, so since it is passing through 0, there will be no intercept. It will simply be equal to I is equal to some slope into t. And what is the slope? 100 minus 0 divided by 2 minus 0 into t. Okay. Since both of them are in milliamperes and milliseconds, you can simply write, you don't have to worry about the 10 to the power minus 3. Okay. Both of them will get cancelled here. So you're going to get I is equal to 50 times t. Okay. So that's what you're going to write here. I is equal to 50 t. What is the unit of I? I is in milliamperes. Remember that. 50 t milliamperes. So you can write this here as well, milliamperes. Okay. And for t greater than 2, it is going to be 100 milliamperes. Okay. So that is what we will substitute in this equation. First we want from 0 to 2 milliseconds. So you are going to get V of t at 2 millisecond is equal to 1 by c is 10 to the power minus 3 integral 0 to 2 into 10 to the power minus 3. I of t is 50 t into 10 to the power minus 3 dt. Okay. So this you are going to get 50 by 2 into t square from 0 to 2 into 10 to the power minus 3. Okay. So this if you solve, you are going to get 100 millivolt. Okay, or 0.1 volt. What about for 5 milliseconds? V of t is equal to 5 milliseconds. So here 1 by t 10 to the power minus 3 from 0 to 2 into 10 to the power minus 3, you have 50 times into 10 to the power minus 3 dt, plus again from 2 into 10 to the power minus 3, that is 2 milliseconds to 5 milliseconds, you are going to have 100 into 10 to the power minus 3 dt. Okay. So this if you simplify, you are going to get 0.4 volt or 400 millivolt. Now we will see the series and parallel combination, what will be the equivalent capacitances. First we will start with the series connection. So here you have capacitors connected in series. Okay. Then what will be the equivalent capacitance? So we take this as C1, C2, C3 and so on till Cn. Now the voltage across this if you take as V and the current through this is I. So the current is same through all of the capacitors, that is the series connection, right? And each of the voltages you can take as V1, V2, V3 and so on till Vn. So now if you apply KVL, what you are going to get? V is equal to V1 plus V2 plus so on till Vn. Now how you can write V? V is 1 by C equivalent integral I dt. Okay, because I is the current passing through all of the capacitors, and if the entire combination if you take as C equivalent, that is what we have to find out. Okay, so then 1 by C equivalent integral I dt will be V. Similarly, what will be V1? V1 will be 1 by C1 integral I dt plus 1 by C2 integral I dt plus so on till 1 by Cn integral I dt. So integral I dt will be cancelled. What will you be left with? 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus so on till 1 by Cn. So that means the reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of individual capacitances. So this is the series combination. Then what about parallel combination? In parallel combination, what will be same? The voltage across each of the capacitors will be same, right? So this is how the parallel combination is going to be. Each of the capacitors are C1, C2 and so on till Cn. Now the current, individual current you can take as I1, I2 and so on till In. Okay, so here you have to apply KCL. So if you apply KCL, then I is equal to I1 plus I2 plus so on till In. Now how can you write I as? I is equal to C equivalent dV by dt. I1 will be equal to C1 dV by dt. So this is equal to, right, plus C2 d V2 by dt plus so on till Cn dV by dt. So dV by dt is cancelled. What will you be left with? C equivalent is equal to C1 plus C2 plus so on till Cn. Okay. Now you can see that this is the result for the equivalent capacitor. It is exactly opposite to resistor. In resistor, the parallel combination had a relation similar to this, and this was the relation similar to series connection. So remember that in the case of capacitance, it will just become inverted. This is going to be series, and in parallel the capacitors are just going to be added. So we will do a few examples, then it will be more clear to you. So we have to find the equivalent capacitance. Two capacitors are in series. Okay. So if you go by formula, 1 by C equivalent is equal to 1 by 1 microfarad plus 1 by 1 microfarad, and this you are going to get 2. So this implies the C equivalent is equal to 1 by 2, which is 0.5 microfarad. Okay. Now remember that you can see one thing here, it is just half of this values. Okay. So when two capacitors are in series which are equal, then you can just write C equivalent is equal to individual capacitance divided by the number of capacitors in series. Okay. So you can take it as the next question. You have C, C and so on till C, n number of capacitors. Then what will be the equivalent capacitance? C equivalent is equal to C by n. Now what about the parallel case? In parallel there are n number of capacitors. C, C and so on till C. They are equal. Remember, we are talking about equal number of capacitors. So equal value of capacitance. Then here what will be the value of C equivalent? This is equal to n times C. Next, one more important result which is worth remembering is when two capacitors are in series. So here what will be the value? Just like two resistors if they are in parallel, then what will be the value? Equivalent resistance. In a similar fashion, when C1 and C2 are in series, you are going to get C equivalent is equal to C1 C2 by C1 plus C2. Okay. So we can do one more problem with actual values. So here you have a 2 microfarad capacitance, and here you have 4 microfarad once again. Now you have two equal capacitances in series. Then what will be the value here? 2 microfarad. Now once again 2 microfarad and 2 microfarad are in parallel. So it will be 2 times 2, right? So you are going to get C equivalent is equal to 4 microfarad.